Hi, I'm Simeon. I'm going to talk to you today about a project we developed at my company, Tweak by Moduscrate, in the last couple of years already. It's called Chainsai, and it's about, as it says, facilitating sampling of multimodal probability distributions. So, you can wait another 10 seconds. This project was built in our data engineering and now also generative AI groups at Tweak. And Tweak is the open source program office of our company, Modus, and we're doing all kinds of things related to digital transformation, big word, but more specifically our group, generative AI, we do a lot of data engineering, software engineering, we do DevOps, but also digital products, I don't know, maintain your conference installation, migrate your GitHub, things like that. So if any of that's interesting to you, feel free to reach out to us. And after this shameless advertisement block, let's jump right in. The title says this service facilitates multimodal probability distributions. Who has heard about multimodal probability distributions? Nice. It's going to be a quick talk. Nevertheless, I'm going to introduce them real quick. So by extension, this also means you have heard about probability distributions, right? So if you work with data, you work with them all the time. And a unimodal probability distribution is what you see on the left-hand side here. It's your standard distribution, for example, Gaussian distribution, beta distribution, what have you. And these distributions have usually one sort of bump or a region with high probability, right? Which is obviously all which is contained in this little bell here. Now, multimodal distributions have two bumps or two regions with high probability, as you see on the right. And examples for those can be mixture models, for example, Gaussian mixture models. So if you take two Gaussians and you mix them together, and if they have different means, you will have, in the general case, two different peaks, right? And an overlap region in the center. They also come up in Bayesian inference. For example, if you have ambiguous data or if there's a mismatch between your prior distribution and your likelihood. And I want to give you one quick example of what I mean by ambiguous data. And that's from protein structure. Maybe not what you were expecting now, but that's unfortunately a bit of my background, so I'm going to stick with that. Proteins are chains of amino acids. And you can do certain kinds of experiments on them that give you distance restraints, which tell you, okay, amino acid A has a certain distance from amino acid B, right? Or on a finer grain scale, certain atoms have a certain distance from different atoms. And this is the case in the left-hand side here. So this data would, for example, tell us this nitrogen atom here is close to either this oxygen atom, O1, or the oxygen atom O2, right? Or both. But we don't know, and there's no way, literally no way, the data can tell us. And if you're doing Bayesian inference, the prior might not tell us either. So this is definitely ambiguous, and this means if we now want to infer a structure for this protein, a three-dimensional conformation of this chain, there's multiple possible structures. And this means the probability distribution over structures given the experimental data is multimodal. Likewise, if we're not necessarily talking about inference, but just about protein folding, proteins, when they fold, they usually have a native state in which they're functional and do their most important job in the organism. Now, if a protein misfolds, you can get serious diseases. For example, prime proteins, if they misfold, you can end up with neurodegenerative diseases like Creutzfeldt-Jakob, for example. And the fact that there's two folding states that are possible, again, means that the probability for a certain 3D structure is multimodal. So those are two examples from more a biology domain. Now, how do we characterize probability distributions? So there's a couple ways for that. Many of you have heard about, I think, variational inference. You can just do, evaluate it at grid points or something like that. But one of the most popular methods is Markov chain Monte Carlo. And the way that works is you have an iterative process where you start at a certain initial state, in this case, for example, x equals 1. And then you propose a state either left or right randomly under certain conditions. I won't go into details here. In this case, we might, for example, propose the state, that's probably something x equals 0. Excuse me. You might or might not then accept this state, and then you propose a new state here, something, what's that, 0.25, and so on and so forth. You store all those states, and then you can build a histogram of those states, which after a while looks maybe something like that. And if you run it for long enough, it will very neatly approximate your probability distribution. So that's the most simple Metropolis-Hastings Markov chain Monte Carlo method. But challenge for all MCMC methods, actually, that use one single Markov chain is multimodality, what we just talked about before. And that's illustrated in this picture. So here we have a bimodal distribution, two Gaussians, and we start off our chain in the bump at 2 in here. And then, as we see in this sort of trace plot, it samples around there essentially all its life and never ever makes the jump into the other mode. So it gets stuck in there. And with a sample like that, we fail to characterize this probability distribution correctly. And what I want to talk to you about today is, in not too much detail, but we can go into those in the questions later, a web service that implements an algorithm called replica exchange or parallel tempering. That's originally been devised in solid state physics in 86 or 85, but somehow hasn't made really its way through to probabilistic programming and the larger Bayesian statistics community. The idea here is that you sample not only your probability distribution of interest up here, which has multiple modes, but also increasingly flatter versions, right? So here, essentially, we just multiplied this probability by a factor, or the log probability, which made it a little bit smoother. Here we increase this factor, or decrease the factor. It's an inverse temperature, what we call it, and it gets even smoother. And at the end, if you keep going, you will eventually end up with a at least unimodal and possibly even somewhat uniform distribution. And those are easy to sample, right? You can use any normal MCMC algorithm to do these. Now, what does that help? Occasionally, you can try to then exchange states between those different chains, right? So you would put the state here, up here, and this one would go down here, right? This one goes up here, this one goes down here. So it's illustrated in the next two sort of frames of this fake video. These arrows indicate which chains are swapped, and in the next step, you'll see that they changed positions. And if you look closely at the 2 points down here, this guy here eventually changed the mode. Now it's in the right mode, and before it was somewhat in the second mode to the left. If you now keep repeating this, and you alternate essentially which pairs you swap, so next time you'd swap, for example, the ones in the middle, then, wrong direction, you will eventually end up with a sampling mechanism that samples all distributions, and in particularly the one you're interested in at the very top, pretty nicely. Can I have the time real quick? 15 minutes. Okay, that's good. And don't be confused if it says structure X here. I shamelessly recycled those from an earlier talk, and I was talking about protein structures before, so please forgive me for that. Now, this algorithm has a couple of problems. I just said that we're using several Markov chains in parallel. And if you want to do that efficiently, you probably need some sort of parallel computing power. And not everyone has a cluster at home. In science, usually this algorithm is run on high-performance clusters in like university data centers. But my laptop can't do this. Furthermore, an important parameter is essentially how to determine the smoothness, right? Like if we scroll one back here, how do we determine like how much do we flatten those intermediate distributions? Like that's a priori unknown, right? And this sort of what we call temperature is very difficult to tune. And that requires experience and often for more complex systems also pretty laborious trial and error. And finally, unless I am mistaken, this algorithm hasn't really made it yet into mainstream probabilistic programming libraries such as Stan, PyMC, or others. And that means if you want to use this, you have to re-implement it yourself and reinvent the sort of the famous square wheel for your own use case over and over again. With Chainsai, we want to address all those challenges, and what's Chainsai? It's a replica exchange implementation on the cloud. So what does it do? It interfaces with existing probabilistic programming libraries, PyMC and Stan. So you would write your model in PyMC, save it in a Python module, upload this to Chainsai, and then our replica exchange implementation would use that model and do its magic, and likewise for your Stan model. It automatically finds a good temperature schedule with a iterative tuning algorithm, which is based on the density of states, in case someone wants to go into statistical mechanics details. And it's on the cloud, so we can easily scale up and down the required computing resources automatically. Furthermore, there's a web interface. It's easy to use. It's essentially a form. I can show that later. You upload a Python file, you hit run, set 2 or 3 initial parameters, and then you're good to go. And finally, you can run this algorithm locally on your computer or on the cloud, and in different sort of versions. You can like just skip all the web interface and logging and database stuff and just run a Python module on your computer. Or you can also deploy the whole service with all the components using Minikube. Or you can deploy to your Google Cloud platform. The architecture, as expected, is somewhat complex, but the really magic happens in the central component here, the job cluster. For each Chainsai job, we have one controller node, which essentially sends out sampling requests to multiple smaller nodes. And each of those smaller nodes here, called rex nodes for replica exchange, corresponds to one Markov chain. And the controller manages all this. And furthermore, does the automatic temperature adaptation. All the components around is essentially infrastructure to manage several jobs at once, to store samples, to store MCMC sampling statistics like the exchange rate, the time steps. There's a logging server, and of course, there's a client web application. There's a lot of tech in this. I keep pushing the wrong button here. And that's our tech stack, right? So on the back end, of course, there's Python. Otherwise, probably wouldn't be here. Only Python. Thank you. Is that with or without the questions? Before the questions, okay. There's a lot of Python on the back end. There's a Postgres database for managing the job database, a user database. Communication between the nodes is done, and you might be surprised to see this here, using OpenMPI. That's because that part is an old research project of mine. We use Kubernetes for container management and Flask to build the HTTP APIs necessary. The front end uses React, and on the whole infrastructure operational side, we use Terraform and Helm for infrastructure as code. We do some package management with Nix, a fully functional functional programming style package manager. You can run all this locally, as I said, with Minikube or on the cloud. So on to an example, soft k-means. So I think most of you know k-means, in which you run a cluster, in this case here, 3 groups of data points. You start out with some sort of random cluster centers, and you assign points to the nearest cluster mean. Then you recalculate the means, and then you iterate over this, and at one point we'll find a sort of, you can split up those points into 3 different clusters, or not so different as you see in this example here from Wikipedia. Now you can do all this probabilistically, right? You can use Bayesian inference to infer the cluster means given the data. So in Bayesian inference, you always ask, what's the probability of my parameters given data and prior information? And this can be translated into a different form using Bayes' theorem. So the parameters would be the means, mu1, mu2, and we have some data, the points. And that's then proportional to a term called the likelihood, which is of the inverse, the probability of the data given the cluster means, plus some prior knowledge or assumptions we put on the cluster mean positions. Now for this data likelihood, we assume that the data was generated from a Gaussian mixture with means mu1 and mu2, but not each of those 2 cluster centers has the same number of points. So we assign unequal weights, which means that those cluster centers are not exchangeable, right? That's not a label switching problem. And we can see the data here in this sort of histogram on the right, where the blue points are generated from one Gaussian distribution and the black ones from another one. Now, if you look at the posterior distribution, the probability distribution for the means, mu1, mu2, we find that it's, surprise, bimodal. So we have a big mode here, the yellow-greenish thing, but also if you can see this, and maybe you can't, there's a fainter mode here. It's a little bit blue, right? So that's bimodal. So a priori, we don't quite know what to do this, and if we just throw a single Markov chain on it, we might get stuck in one of the modes, and in the worst case, actually in the sort of worse or less probable mode, and we will never get out of that. So that's how to sample with one chain. And then using Chainsai, we find that the Markov chain actually jumps easily between those 2 modes. And thus this problem is a piece of cake, and that's why this little guy here is super happy. Now to see what sort of influence on the actual clustering results this has, we can look at a measure called the responsibility. And that's essentially a quantity that tells you for each data point how strongly a given cluster center, in this case cluster 1, cluster 2, explains a data point. And here I want to keep you in mind that cluster 1 is centered at 0, and cluster 2 is centered at 1.5, while the data point here is at minus 0.5. Yeah? Now, if you look at these graphs of the responsibility, right, we find that for cluster 1, the sort of darker shade here, we have very low responsibility values. And that's wrong, right? Because x equals minus 0.6, very much closer to 0 than it is to 1.5. While we have high responsibility for the cluster 2 for most of the samples. So this means we're stuck in a local minimum, and worse, even the less important one, as I just showed you in the 2D histogram. So that's not a great result. Now, if we use Chainsai and we plot the sort of histogram of responsibilities over all samples, we find correctly high responsibilities for cluster 1, so the sort of brighter shade here, centered at what's that, maybe 0.1 or something. So 10% probability, so to say, and a low probability for low responsibility for cluster. Sorry, I mixed this up. So this is cluster 2, the big one, which is correct, and high responsibility for cluster 1 in this large peak in this histogram. So that's already better. We hit the big mode instead of the small one, but even better, we even have a small probability here that the reverse is also possible. Yeah. So we have smaller peaks here for cluster 1, and on the right for cluster 2, which would be the smaller probability mode. So that's a better result. It characterizes the probability distribution much more honestly. And I want you to think about what the implications are when you miss a mode, right? So if you say, hey, the big mode might correspond to this patient does not have cancer, and the small one means, well, okay, there's actually a certain probability, they do. So I'm pretty sure you agree you actually want to have both modes, right? So if you if you suspect that your probability might be multimodal, you should make an effort to try to characterize it correctly, because you might miss out on important information. So that's pretty much the end. There's current issues and things to do, of course, as with any big project. In the big picture, we started building this already something like 3 years ago. It's an ambitious project. As you see, there's many components. And we did some market research, maybe not enough. So we thought, okay, if you build it, they will come. Turns out they didn't. So we desperately need real-world use cases. So if you have multimodal probability distributions in your job, in your hobby project, do reach out to us. Maybe this could be useful for you. And if not, maybe we can work together to make it useful. Currently, as we have had little feedback from the community, we don't have too much resources for active development, but we'd be more than happy to maintain. And if it turns out that this is useful, right, then there's a good chance that we might step out our game here. As for features, it only does very basic single chain sampling, so using just a very naive Hamiltonian Monte Carlo. And one of the big opportunities would, of course, be to implement state-of-the-art samplers like the no U-turn sampler NUTS, which is implemented in Stan, PyMC, and every other state-of-the-art package. As for issues, as we don't develop much on this, the code is rotting a little bit, and I think being discussed a lot in this conference. Docker images need constant updating. Python dependencies can break. Recently, there was a story with PyYAML, which broke like 1 billion things, and that is an issue, but all those are easy to fix. I have 1 minute left. Here's some credits. So most of our thanks to the amazing Chainsai team. If you run across any of those people, Doran, Said, or Etienne, and many others, in the course of your career, please do hire them. They're not with our company anymore. They're amazing. Thank you for your attention. And I stole a lot of stuff from different sources on the internet, and the attributions are on the right. And there's lots of resources, GitHub repositories with the code. We have a website. Currently, the service is not deployed, so the code mostly contains links. But we have a couple blog posts on tweak.io/blog. If you look for Chainsai, there's 4 or 5 blog posts and all the information you ever want.
Great. Thank you very much for the exciting talk. I'm a little bit confused of what's the input to these algorithms typically, because I think in regular MCMC you have a function which is proportional to your probability distribution, but the problem is you can't normalize it because it's high dimensional, for example. But here, is that also the case, or are you trying to go directly from some sample data you have into producing similar data to that, or sort of what do you initialize your, in the API maybe, what do you initialize your algorithm with?
Yeah. It's exactly the same input, pretty much, as can I do this full screen? As your standard Hamiltonian Monte Carlo or something, right? So all you need to provide is a probability distribution. So you need a log probability function, and if you want to do useful stuff, you also need a gradient, right? And there's currently no, I mean, for the simple sample there's no autodiff implemented, right? So you would have to bring that yourself. But if you have your model in PyMC or Stan, of course, we reach out to those libraries to do the gradient calculation for you. So in that case, just a PyMC or Stan model. Exactly the same input as for any other PPL. Plus, and I don't know why does this keep popping up. I don't know why this is kind of blurry. You need to give a couple parameters, for example, the maximum number of chains you want to simulate, right? Because it's a cost factor as well. You can set the minimum temperature, right? But those are just, you can try out those values a little bit, but all the rest gets adapted automatically in an iterative scheme.
Yes, thank you. My question is about MCM. If you vary the initialization points, can you avoid the local minima? Try 50 initialization points.
You can, and in fact, that's what many libraries do, like PyMC or Stan. You can, what they do is they sample maybe 4, 6, 8 chains in parallel. But you're not guaranteed that those actually hit all the local minima, right? If you have 5 minimas, you have 4 chains, and you can't escape, then there's going to be 1 minima left that you don't hit, right? While with replica exchange, you have this scaling problem much less. If your temperature schedule is sufficiently well adjusted, and your flattest distribution is sufficiently flat, then you will get all of those. Local minima.
Thanks for the talk. You showed a quite complex deployment with many components on the cloud. But is there a library that you release, like standalone, that would do the simulated annealing, which I think is the...
So a little nitpick here, it's very much related to simulated annealing, but it's a valid MCMC algorithm, right? So it gives you statistically valid samples, while simulated annealing is an optimization method that gives you technically only the global maximum. But apart from that, yes, this central party, the controller, so it's everything in this job class that you can run on your local machine without Kubernetes, without any databases. There's instructions for that in the GitHub repository. Of course, you're limited to what your local machine has to offer, right? If you have 8 cores, you have to do with that. But for testing it out for small problems, that might do the job. So that's definitely possible and not too hard either. It's a teeny bit of manual work, but we have instructions for that in the repo.
Thanks.
Any other questions? Yes. Let me run over.
Thank you for the presentation. Do you have any plans to extend your package on random fields, for example, or other random distributions parameterized with certain parameter?
I personally would love to, we would love to, but for that we would need use cases, and as this is still a company project, we need people who use it, right? I mean, I'd personally be delighted to implement this. I'm very passionate about it. But if we're not sure that this is something the community requires, then it's going to be hard for me to convince my bosses to put time into this, right? But if you can make a good use case and maybe bring a couple friends, then there's a good chance we might get to that, yeah.
Okay, one last question and then the lunch break.
Yes, thank you for the talk. So from a user perspective, if let's say I want to use your tool, I suppose, if I understood well, I cannot anticipate if I have a multimodal beforehand and if I explore all the space. But let's say I'm using PyMC and I do some conversion check afterwards and I see that my chains didn't converge, and repeatedly that's the case. Can that be an indicator to maybe use your tool, and then how can I proceed to do that?
Yeah, definitely. If the convergence criteria in PyMC tell you that there's probably issues, that would be a good indication that maybe you have multimodality, which in this case often means like you end up in different modes, in different runs, in different chains. In that case, it's really very simple. You submit a Python module with the PyMC import in which you define your model. It has to expose a certain API, right? So this module has to expose like a function log prop and a function, not even that, right? And only the log prop function, and then our sample will call PyMC, autodiff, and other methods to use your model out of the box.
Okay. Can we thank the speaker again, please?